the universe. For all we have learned about it, we have still only scratched the surface. Everything that we can see around us makes up less than 5% of what's actually out there. All the rest is called dark matter and dark energy. What are they? We still don't know, even thought they determine the fate of the universe. We have confirmed over 3,000 planets orbiting stars other than the Sun, but most of these extrasolar planets are huge and very close to their host star. How common are planetary arrangements like our own? And how many planets in our galaxy have the potential to harbor life? These fundamental questions are part of what drives NASA science, and they spur the development of new space observatories. WFIRST, the Wide Field Infrared Survey Telescope, is one of these. Nancy Grace Telescope is built on an existing telescope that is very similar to Hubble, but with the added benefit of 25 years of technological development. The Wide Field instrument is the heart of the Nancy Grace Roman Space Telescope. It is what allows the Roman Space Telescope to take pictures with the same detail as Hubble, but covering an area 100 times larger. Despite this incredible power, the basic design is the same as telescopes around the world. Light enters through Roman's 2.4-meter aperture and is reflected and focused by the curved main mirror, which is also the largest mirror in the telescope. This light is reflected and focused once more by the secondary mirror. More elements tighten the beam and strip it of stray light rays before it passes through the filter wheel. This wheel has a variety of filters that allow different wavelengths of light to pass through. It spins from one to another depending on what the researcher is looking for. Finally, the focused and filtered light reaches the focal plane, where it creates an image on the detectors. These detectors use the photoelectric effect to convert photons into an electrical signal that is then decoded into an image. In Roman's case, there are 18 detectors, allowing it to create 300 million pixel images of large patches of the sky. The large number of detectors and pixels gives Roman its wide field of view. The size of the mirror and the precision of its optics gives Roman its fine imaging. This combination of image size and detail has never been possible on a space-based telescope before. Nancy Grace Space Telescope will lead the push to understand dark energy, a mysterious pressure that is making the universe expand ever faster. Dark energy makes up 68% of the cosmos, and its properties, whatever they are, determine the fate of the universe, but no one knows what it is or exactly how it behaves. Another mysterious component of the universe Nancy Grace Telescope will study is dark matter. Dark matter accounts for 27% of the cosmos, 5 times as much as the matter we can see, but has remained invisible to us. We can detect it by seeing how its gravity warps light from distant galaxies, a process called gravitational lensing. Nancy Grace Telescope, powerful 2.4-meter telescope, will also help us in the search for extrasolar planets or exoplanets. Using the same gravitational lensing principles, Nancy Grace Telescope will watch for so-called gravitational microlensing events, a unique light signature caused when a planet and its host star pass in front of a background star. This technique extends planet detection capabilities to smaller and more distant worlds than other methods, so it can catch ones that have eluded us before. Nancy Grace Telescope enormous field of view will allow scientists to watch huge portions of the Milky Way for these microlensing events. As a result, they will be able to complete the census of exoplanets begun by Kepler. To deepen its study of exoplanets, Nancy Grace Telescope will also be outfitted a beyond state-of-the-art coronagraph. A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear, while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own. Nancy Grace Telescope Coronagraph will directly image and analyze Neptune-sized planets in orbits slightly greater than Earth's. Existing coronagraphs can only image larger planets that are much more distant from their host stars, so this new capability represents a dramatic improvement. In order to make all these measurements, Nancy Grace Telescope will move to nearly 1 million miles from Earth and orbit a special area of space called a Lagrange point. This particular point, called Earth-Sun L2, is one of several locations where the combined gravitational effects of the Sun and Earth create a zone of stability where a spacecraft can pace Earth as it orbits. Nancy Grace Telescope will be a way to answer many of the biggest questions about the universe. Questions like, how does the universe work? And are we alone? Its wide-field view and coronagraph will complement missions like the James Webb Space Telescope and the Transiting Exoplanet Survey satellite, TESS. Nancy Grace Telescope will be an indispensable part of space science during the next decade and beyond. While thrusters are great for moving a spacecraft around, they aren't as good or efficient at controlling where the spacecraft points. Instead, rotating wheels and conservation of angular momentum make it possible to turn in any direction without any outside influence. Most space telescopes, from NASA's Hubble to Webb and everything in between, use components called reaction wheels to change where they are pointing. The reaction wheels run on electricity. Unlike thrusters, which are less precise and can run out of fuel, the reaction wheels are basically flywheels driven by electric motors. They spin to store angular momentum. By slowing or speeding the rotation of a given wheel, changing the amount of momentum, a computer can precisely adjust how the spacecraft points around its center of mass in one plane. With 3 wheels set at specific angles, a satellite can control its pitch, roll and yaw to point in any direction, and then hold that position without any change. NASA's Nancy Grace Roman Space Telescope has added its set of reaction wheels to the main spacecraft body, or bus. Roman has 6 reaction wheels, rather than the necessary 3, to give it more angular momentum for faster pointing, as well as complete redundancy should any one wheel fail. Each of Roman's wheels is 18 inches across, about the size of an extra-large pizza, weighs roughly 45 pounds, and spins up to 4,000 RPM. As long as the solar cells provide them with electricity, the reaction wheels could repoint Roman indefinitely, except that they have one function requiring thrusters. The reaction wheels counteract the pressure from sunlight, which exerts a tiny but steady force that, over time, would push Roman out of alignment with whatever it is observing. The wheels can exactly offset that pressure by slowly spinning faster. When a wheel finally reaches its maximum rotation speed, it needs to unload or slow down so that it can begin to freely vary its speed again. Roman engineers gently fire specific thrusters, causing the maxed-out reaction wheel to compensate the rotational force by slowing down. Thrusters are also critical for any action that physically moves Roman. Reaction wheels can only rotate the spacecraft in place. They can't cause a change in location. Fortunately, Roman's extensive set of thrusters will be well-fueled and fully up to the task, positioning the spacecraft and unloading momentum so that the reaction wheels can keep it perfectly pointed at the stars. As we look to the stars, the Nancy Grace Roman Space Telescope stands poised to revolutionize our understanding of the cosmos. Scheduled for launch between October 2026 and May 2027 aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center, this mission aims to unveil the mysteries of dark energy, explore distant exoplanets, and peer into the early universe. Reflecting on Dr. Nancy Grace Roman's legacy, she once remarked, "If I hadn't been stubborn, I would have been talked out of it years earlier." But launch schedules can be unpredictable. What do you think? Will the Roman Space Telescope launch on time? Share your thoughts in the comments below. Thank you for watching. Don't forget to subscribe and give us a thumbs up. It really helps us out and doesn't cost you anything. More incredible videos are coming your way. Remember, the universe is vast, mysterious, and full of wonders waiting to be explored. Stay curious, keep looking up, and until next time, keep your eyes on the stars.